Julian.
Okay, so how's everyone feeling?
Totally awesome, sir.
So, we have some pictures here of the moon going around the Earth, and it's just fascinating to me. Thanks for spoiling me.
Well, it's recording, so if we don't finish today, they have to, kind of like last time with Roger.
All right.
Java. Wait, where's Jeremy now? Oh. Shall lower the volume.
Okay, so. Whoa.
Regular checker.
So, here we go. What keeps the moon circling the Earth? Now, basically, I always think of the year Newton was born because he was born 300 years before the year my dad was born. My dad was born in 1942, and Newton was born in 1642. And apparently, I'm not really sure what happened to his father, but between the time his mom got pregnant and the time he was born, his father died. So Newton never knew his father. And then, even sadder yet, Newton's mom remarried and got involved with, another man. So she gave Newton to other relatives to raise. Because she wanted, I guess, to start a new life with another person. So poor little Newton, you know what I'm saying? And he grew up in an area of England where there was a lot of farms. He lived on a farm. And apparently he was just an average student. His teachers commented that he was inattentive. He used to like building things at home. He built a windmill that helped grind the corn. He built a mechanical clock. But basically, once he graduated high school, he planned on becoming a farmer and just, doing the thing, he'd been doing as a kid. And basically, it was one of his uncles who, I guess, saw that, he was pretty good at, putting things together and figuring things out. So he suggested Newton go back to college, and, so he encouraged him to go back. And so Newton decided he was going to be a lawyer. And he went back to become a lawyer. And the first couple of years of college, he had to take all law courses and political science courses and things of that nature. And there wasn't any freedom to choose any electives. But then in his third and fourth years, he was allowed to take some electives, and that's when he started to take some math and science courses. But he graduated with a law degree, and then shortly after that, it wasn't the Black Plague, it was the bubonic plague. The bubonic plague. And basically, it was a pretty serious deal. I guess over 100,000 people died from this plague. 20% of the population of London died from this plague. And basically, it it was some kind of bacteria that was just spreading all over, and the only thing you could do to protect yourself is just to stay away from other people. So basically, Newton took refuge at his uncle's farm, and basically it is known that during that stay on his uncle's farm, he discovered the three laws of motion: law of inertia, F equals ma, action-reaction. He discovered the law of gravity, which is what we're going to learn about today. And in order to do this physics in a sophisticated manner, he developed a whole other branch of mathematics. Say it loud, JD. Yeah, calculus. And all while he was just independently by himself, isolated. So it's just kind of weird. I guess it was 1665 when all this sort of started to happen, and something just clicked, and it all began to work for him. I guess eventually, not only did he become a professor, but he was also a member of Parliament, which doesn't surprise me because he had that law degree, and he was involved in many different things, but he never married. He was never had a girlfriend. I thought, when I first was reading that maybe he was gay, but I never saw anything written that he was gay. I think he just wasn't interested in anything like that, so he was just all about physics. Yeah. So, what I've shared with you folks is true. This next little bit is kind of like a legendary story. Whether it's true or not, who knows. But I want to share the story with you the way it was presented to me, and basically how Newton discovered the law of gravity. And it wasn't like he dropped something and, whoa, what? Things fall, and no one noticed. No, it was much more than that. And basically, here's how the story goes. Newton was out working in his uncle's apple orchard. And so this is an apple tree. It's not drawn to scale. And this is the earth. That's the whole earth down below. And basically, Newton had a ladder and he was up in the tree picking apples. And through the branches, he saw the moon out during the day. And sometimes you can see the moon out during the day. It's easier to see at night, but nonetheless it's out during the day. And Newton knew that when an object went in a circular path, there had to be an inward force acting on an object. Anytime an object went in a circular path, there was a force acting towards the center of the circle. Otherwise, the object wouldn't continue in a circle. It would just go off tangentially in a straight line. And one of the questions at the time was, if the moon is circling the earth, what's providing that inward force keeping the moon going in that circular path? That was an unanswered question at the time. So there Newton was, picking the apples. He reached for an apple off the branch, when an apple higher up fell off the branch, was coming straight down towards his head. He saw the moon through the branches, and then it hit him. The same exact force that pulls down the apple is pulling down the moon. The weight of the apple is pulling it down. Well, the earth isn't just pulling down the apple, the earth is also pulling down on the moon. So basically, he discovered, or he proposed, the same force that pulls down a falling apple pulls down on the moon. And Giselle, what is that force that pulls down an apple?
Gravity.
is the force of gravity, yes? So Newton determined that it's the force of gravity that's pulling in on the moon, keeping it going in a circular path. Now, of course, when Newton published this, he knew that there was going to be an immediate question. And what do you think was the immediate question that other scientists and other people asked? When he said the same force that pulls down a falling apple pulls down the moon. Jeffrey?
How the heck is that possible?
That was good. That was good. More specifically, right? With that?
What is that force?
Well, he knew what the force was. It was the force of gravity. So, just like gravity pulls down the apple, gravity was pulling in on the moon. Okay, so I'm sure all these questions were asked, but there was like a big question that, Michelle? Exactly. Newton, if it's the same force pulling down on the apple, why doesn't gravity pull the moon into the earth and smash it into the earth just like the earth pulls in the apple? So that was the big question.
I know, that was Transformers. I think Floyd had a dark side. When I leaned back,
So Newton was prepared to answer this question. As a matter of fact, the diagram that I'm going to draw next for you is very similar to the diagram that he drew in his book. It's called like the Principles of Physics. And basically, he drew a diagram that was way out of scale and looked something like this. Here's the Earth. Here's a mountain on top of the Earth. And of course, the world's largest mountain, Mount Everest, would not even be seen as a blip on an Earth this size. So this is like way, exaggeration. But nonetheless, for educational sake, imagine this huge mountain on top of the Earth. And imagine that on top of that mountain, there was a cannon that could fire cannonballs really far. Yes? So basically, if this cannon could shoot out horizontal projectiles, what would the horizontal projectile do? Well, here's the cannonball coming out of the cannon, and basically, we study projectile motion. It would end up taking a parabolic path back to Earth. Just like this, when we studied projectiles shot from the top of a cliff. Basically, what does the projectile do if it's shot horizontally? Going down like this. Yes? We know that the forward motion, is uniform. Nothing to speed it up, slow it down in that direction. Meanwhile, the direction this way is accelerated. Yes?
You want to copy the diagram with the cannon firing?
Yes. So basically, same held true for this. As that cannonball went, the motion parallel to the surface of the Earth, that was uniform, and the motion perpendicular to the surface of the Earth was accelerated. Projectile motion. Been there, done that. So what's your point, Newton? Newton went on to say, what if the cannon was shot with a faster horizontal projectile, with a faster horizontal velocity? So here we go. Again, this is ridiculously far, but if it could be shot that fast, that's exactly what would happen. Okay? Just like if it was thrown faster over here, it would go, What happened to my signal? Again, we know that that projectile is being pulled down by gravity. If it wasn't being pulled down by gravity, if gravity wasn't acting on it, as soon as it was shot out, what would it do? It would just keep going in this direction. But no, gravity was definitely pulling in on it. So both of these had the force of gravity pulling in on it. Yes? Newton went on to say, all right, what if the cannon was shot with an even faster horizontal velocity? Falling, 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 falling. Let me try this again. Just like the other two, it's being pulled in towards the Earth. Now, if at this point, if the Earth disappeared and wasn't pulling it inward, what would that projectile do? It would just fly off this way, yes? But no, it doesn't fly off that way, because the Earth is still pulling it inward, yes? So basically, the Earth is pulling it inward, and it is falling, and falling, and falling. But here's the difference. Over here on this diagram, the surface of the Earth is drawn as flat. And if you throw it out even faster yet, it comes and lands on the Earth, yes? But with this larger scale, the ground is like curving away from the projectile. Look, the ground is curved because the Earth is round. So even though the projectile is falling in towards the Earth, the weird thing is, the Earth is curving away from it at exactly the same rate. So in the end, even though it's falling, 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 it actually never gets any closer to the Earth. And if the cannon was removed, it would just keep going round and round and round and round. And basically Newton said, that's what the moon is. It's not a cannonball. It's just this big rock that was thrown with the just right horizontal velocity. And it's going around, and the Earth keeps pulling it in. Let's see if I can get this link to work. It's going, it's loading. Let's just see if it'll load. Alright, I think I'm going to have to switch computers because I can load on the school's computer. So I'm going to have to end the recording here.
Oh no,
Jeremy, we're back! Here we go!
Where's the white string?
Don't listen to them. Not quite fast enough.
Do 4,000.
Oh my goodness.
What was it? 4,000?
200.
I'm just getting very hungry.
Oh.
It's falling, it's falling, it's falling, it's falling. Oh my goodness, but it's not getting any closer. It's not getting any closer. But no, it is falling, it's falling. No, but it's not getting any closer. Oh my goodness, oh my goodness. And it just keeps going round and round and round. So, ladies and gentlemen,
I don't really know Russell Brand's voice.
now, what we're going to have to talk about next week is the next logical question. Whoopsie.
Whatever happened to Russell I don't.
We know that the moon has that just right horizontal velocity. If it was thrown any slower, it would crash into the earth. If it was thrown any faster, it would just be like, bye-bye. So, what do you think the next natural question scientists ask? Giselle? That's a good question, and that's what we just had right there. Yes?
How does it maintain the horizontal velocity?
Well, that's an excellent question. That's an excellent point to raise right there. Can anyone in the class address that? How does it maintain its forward velocity? Nicole?
Because the horizontal velocity is not affected by the vertical velocity, so it's horizontal velocity is going not horizontal, perpendicular velocity is going down.
Exactly. So why does it keep going forward, even though there isn't a forward force pushing on it? Inertia. Okay, excellent question, excellent answer. The moon is thrown at that just right velocity. What's the natural question to ask? How was it thrown? How did the moon get going at that just right velocity? So we're going to have to address that on Monday. How did the moon get its just right, perfect horizontal velocity? But you have to admit, isn't that amazing? Now, every time I look at the moon, I'm like, oh, there's that soccer ball going across the sky, because that's all it is. It's a big rock going across, being pulled in. Amazing!
It is.
So that's why.
Yes.